Okay, hello AT finite students. I'm going to try to do one of these RSA schemes for you. I'm going to start with the one that we started in class today from the For All Practical Purposes book, and then I'll try to do the one from the other book as well. Okay, so picked distinct very large prime numbers. Well, it says that you should pick prime numbers just for like that added feature of internet security, but for our purposes, for our purposes, I'm going to choose smaller ones, relatively small ones, so they're just not crazy. So I'm going to let P be 31. I haven't done this in a while. And Q be 29. They're primes. They're not huge, but they're not tiny. It's not like I picked 2 and 3. So I picked pretty good prime numbers. And that makes N 899, which is kind of a cool number. Okay. This number is called the key. I like how they have this little hint in here that they didn't do so well in the book. Anyway, compute the least common multiple of p minus 1 and q minus 1. Okay, so we're talking about least common multiple of 30 and 28. And actually we'll call that that's called the LCM. Awesome thing about our calculator is you can actually type LCM and just kind of do this 30 comma 28, and it'll just do it. If you really want to know where that is in the menu, you go menu number, yeah, that's right there, least common multiple. And oh wait, it didn't work. Whoa, sorry, mouse problem. Do that again, menu number least common multiple. It just, yeah, it does the same thing. So that's where that comes from. It's actually about or even fewer keystrokes to just actually type LCM. That's 420. All right, so whoa, sorry, wrong page. So that's 420. We're going to call that M. All right, pick R so that it has no divisors in common with M other than 1. So another way to call it is relatively prime. So it doesn't have any of the same common factors as 420. So one way to think about that is that if I tried to do the LCM of my number R and 420, it would be 1. I did this in class, and I was thinking the quickest way to figure out that something's not going to have the same factors as 420 is, well, let's look and see what the factors are of 420. So you go to number, you go to factor, and this is why I want to do this video, because our calculator has a lot of cool features on here. Okay, so these are the factors of 420. So things like, 2 goes into it, 4 goes into it, 3 goes into it, so that means 12 is going to go into it. So those are all things I can't have be factors of my other number. So one way to pick a number R that's not going to have any common factors is just pick another prime that's not in this list. Well, this is all the primes up through 7, so if I pick something like 11, it would work. But I can't pick anything like 8. Like I can't pick any even numbers because those have factors of 2. I can't pick anything that's a multiple of 6 or a multiple of 15 or 10. So if I just pick 11, I know where I'm going to be fine. So let me pick. Actually, you know what? In class, I was working on this with Christine today. We picked 13, so I'm just going to pick 13. I could pick 11. I thought I'd pick 13. Oh, yeah, because I think in the book they pick 11 on theirs, and I just wanted to be different. So we can pick 13. Okay, any such R will do. Well, sometimes they're kind of hard. It seems like they make this sound like you can just kind of pick any number. Well, you can't just pick any number. You got to pick it so that this happens, which is kind of a big deal. Okay, find S so that RS mod M is 1. This is actually kind of tricky. It says to find S, simply compute all these different powers of R, R to the sum power mod M, until you get R to that power mod M equals 1. And then the power just before that is what S is going to be. Okay, the power of R right before that mod M is what you're going to use for S. This is way easier said than done. Okay, so remember my R is 13. I'm looking at mod, and again, mod is easier to type, but if you want to know that it's actually in the menu somewhere, it is, was it in number tools? Yeah, mod, that's way easier just to type the letters MOD. But if I go, okay, mod 13, 420. So I'm basically finding 13 mod 420. That's not going to be 1. So I start raising 13 to successive powers. I'll try 13 squared. Notice how I'm doing this. I'm just copy pasting that down, go back in here and change the exponent. I keep doing this until I get an answer of 1. This seems pretty crazy, but it actually happens right there at 4. So the answer I want to use for this is the answer to this one. The number I'm going to use for S is the previous powers mod number when I did that. So it's going to be 97. So it turns out that 13 cubed mod, I'm going to write this down so you can refer to it later, mod 420 happens to be 97. And so 97 is what I'm going to use for S. Whoops. What I'm going to use for S because, and this is because 13 to the 4th power, that's a 4. This is not as easy as it used to be. Okay, 13 to the, or as it should be, 4 mod 420 happens to be 1. So since that's where I hit the 1, that's how I know, okay, I need to go back one, and that, whatever that mods out to, that's going to be my value for S. Okay, publicly announced, this is also good stuff. Publicly announced N and R. So I'm going to tell the world that my key involves an 899 and it involves a 13. But keep PQ and S a secret. That has to do with being able to, first of all, know how to factor this and this other stuff, which is going to come back later. Okay. Convert the message. Oh, yeah. So then I have to have a message. So let's pick a message. Okay, I'm sick of not having this around, so I went ahead and found it. This is, and I'll put this graphic on your quiz and test because I just don't want to bother counting all the time. So this is going to be this is my chart to go from 0 to 25 for the letters, and I'm going to start with the word finite. Let's convert that to numbers. So if I convert those into numbers, this is what I get. Okay, then it says break up the message into uniformly sized blocks. Okay, I did this once already and I messed up. What happens is, okay, so if I notice I have 8 digits here. If I break this up into 2 blocks of 4 digits each, these numbers are not in the set of, and it explains this better in the other book. These numbers are not in the set of elements of the mod 899 that we're going to use. In other words, these have to be broken up into chunks, into strings of digits that are basically smaller than 899 or smaller than 898. So I could use, so I can't use 4-digit strings. I actually learned a lot in the fact that turned out to be a problem later, so I feel like I'm a lot wiser already. I'll tell you about that later. So let's just start by breaking these into blocks of 2. I could do 3, but then if I ever have a 9 in the hundreds place, it could be a problem. So I'm just going to do blocks of 3, and it'll look like this. M1, we're going to call 581. M2, we'll call 3. Oh, wait, I said 2, didn't I? Geez, and then I did that. So 5-8, so 2 digits. And then 1-3, and then M3 is going to be, what do I got, 8-1. And then M4 is going to be 9-4. Okay. So, I'm not ready to send this yet. I have to still encrypt this. Check to see that all greatest common divisor of each M, I, and N, that's an N if it's hard to read, is 1. So basically I need to make sure that these things are relatively prime with 85, so that none of these have any common shared factors. Great about our calculator is it actually does that. So I'm looking at 58 first. I have to make sure that it has no common, what was it? They want greatest common divisor. So if you go in here, greatest common divisor, or you could type GCD, 58 and 85 is supposed to be 1, and it should be 1 for all of these. 13, 81, and 94. Let's just check them all quickly. 13, that's going to work. 81 and 94. I think we're fine. If you have really big primes that you chose in the beginning to get that 85, if you chose really big primes for your P and Q, there's no way this is going to have any common factors. It's just going to be too rare for that to happen, so you shouldn't have to worry. I lucked out. I did okay with my 29 and my 31. Okay, so that's done. Oh, you know what? I'm going to put this here. There we go. So another thing I got smarter about when I was taking my little vacation making mistakes here is that I can copy paste these right in from the calculator. So there you go. So that's how you check to make sure all those are going to work. So that's great. That worked. Okay. Now this is a little innocent looking step here. It says calculate R sub I, like convert each one of these. This is the actual encryption step by taking each one of them to the R power mod n. So let's go back in here. I'm going to take, I think it's easier to just say mod that, 58 to the, now remember this was to the R power. Now what's R? R was the other thing that was broadcast to me. That's a 13. 13 and mod 899. Now some of these are huge numbers, but luckily our calculator just does this for us. What else we got? 58, 13, 8, oh, they're up here. 13, turned out to be R, that's just kind of a coincidence. 81, and what I'm producing now is the actual encrypted string. So what those are, let me put those in there for you also. All right, so copy pasted from the calculator. I took each one of those to power of 13, which is R, mod 899, and this is actually my encrypted message. So at the end of that, we'd actually send this. Now, I'm not really sure yet. Does the receiver have to know where the spaces go in this? Would I have to send this as a 029? I don't really know. We'll kind of see how that goes when we get some more examples in there. Oops, hope you didn't see that little number there. All right, so now we go back to the role of the receiver. The receiver has received this message. For each one of those RI, so each one of these little blocks of numbers, each one of these little strings. And I know I said I was going to change these into sets of 2 digits, and that was really to make sure that they were part of the set of elements that are kind of legal in the mod 899 world. These are also legal in the 899 mod world because they're all less than 898, including this 879. So they can come out that way, fine. They're never going to get encoded as 3-digit numbers, but that's okay. Anyway. So I think inherent in this transmission code, we do have to tell the receiver that there are 4 separate things. And I think that's kind of inherent in these instructions when they say we're talking, it's like separate for each message received RI. So the receiver would know this isn't just one big stream of digits, it's actually 4 blocks. Okay, so then now notice we're taking each one of those to the S power. Remember, S was one of those secret things. S is the 97 that's secret. We're gonna take each one of these to the 97th power, mod 899. So let's do that. 29, that's what we're doing now, mod 29 to the 97th power, mod 899. And guess what? That should, what I do? Oh, I'm still in the exponent. That should, I was getting excited. That should come out as the original 58. Did it work? Did it work? Did it work? Oh, good, it did. It came out as the original 58. Okay, I'll do the rest of those and copy paste those in. And oh, great. So this is the message that the receiver received. Why is that great? That's the message that the receiver receives. It's these 4 things right here, which guess what was the original, before I started doing the encryption, that was my method, or my original message in the first place. So that worked out great. I'm going to go ahead and stop this video now because I think I'm limited to 15 minutes, and then I'll make another video for the other one. Also, in case that one's totally better or worse than this one, we'll have them as 2 separate videos. Okay. Just one last thing, I didn't convert this back into the letters. So again, this would be the final message that was received, which was like this, and the person would have to know somehow that this 58 works out as a 5 and an 8 and not a 58. And this, but even more important, I guess, is that this 1-3 is a 13 and not a 1 and a 3. So if you were able to somehow transmit that information also, which again we'll look at when we do more of these examples. Again, it was the original message I encrypted in the first place. Okay, on to the other video.